Hi and welcome to this video. In this video, I want to take an example. I want to think about how we can go about designing a system that would measure our body temperature. Okay, uh, so if we want to measure the body temperature, let's just think about the range of the body temperatures. Now, normal body temperatures would vary somewhere between 36.5 degrees Celsius to 37.5 degrees Celsius. However, if you have you can go above or below these limits, right? Because this is just the normal body temperatures. But if you go as far as 32 degrees Celsius, then you are most likely dead because it's too cold. Uh, Human beings don't have as low body temperatures as 32 degrees Celsius, even though your limbs may at times go to temperatures that are there or maybe even lower. Okay, and you don't go above 42 degrees Celsius. The human body temperature doesn't go above 42 degrees Celsius. So let's say the range of our body temperatures is between 32 to 42 degrees. That's what we want to measure. Uh, I thought I'm just going to use a sensor called the TMP35. Now, a TMP35 is a sensor that outputs voltage which is proportional to the temperature, and the scale factor is 10 millivolts per degree Celsius. Okay, and the way TMP35 works is at 25 degrees Celsius, it will give you a 250 millivolt output, and then the scale factor, which is 10 millivolts per degree Celsius, right? So basically, the equation to get temperature is very, very simple. So if you get a voltage in millivolts, you divide that by 10, and that would be the temperature in degrees Celsius for this particular sensor. Okay, so which means that for 32 degrees Celsius, you will have an output of 320 millivolts, and for 42 degrees Celsius, you will have an output of 420 millivolts. Now, if we are designing a medical instrumentation system, if what we want our system to do is measure the body temperature, and thus our sensor is TMP35, and we want to use an ADC to convert this voltage. Now, the output of our sensor is only going to take voltages between what range? 320 millivolts and 420 millivolts, right? And what we want our signal conditioning circuit to do is to convert this 320 to 420 millivolts into the full range of our ADC. Okay, so uh, so if we assume that we are going to use a 8-bit ADC with a range of 0 to 5 volts, you can see that each level, okay, we are going to have 256 levels because this is an 8-bit ADC, and these 5 volts are converted into 256 levels. So each level is going to be approximately 19 millivolts or 19.5 millivolts wide. Yeah, and that's what we see here in this diagram. And what we want is our analog input, so here is 320 to 420 volts, to be converted into digital using this ADC. Let's assume that we don't use a signal conditioning circuit right at the beginning. So what would happen then? What would happen is uh, these levels will be converted by the ADC into digital values, but you will only use 7 levels here. Okay, instead of 256 levels that you have to convert the temperature, you're only going to be using 7 of these levels, and you can then calculate the resolution of your measurement, right? So the resolution is going to be approximately 1.9 degrees Celsius. So you have divided the 32 to 42 millivolts range into 7 parts, and you can evaluate the resolution, and this is going to be approximately 1.9 degrees Celsius. Now, how do we improve the resolution of measurement? How do we make a signal conditioning system that is better than this? Because 1.9 degrees Celsius is quite a lot, right? If you're measuring body temperatures, 1.9 can be the difference between normal body temperature and a reasonably high body temperature where you are really sick. So you want a better resolution. So how do we do that? One way of doing that is by using a signal conditioning circuit. Now, what do we want our signal conditioning circuit to do? We want a signal conditioning circuit to convert this 320 to 420 millivolts range, sensor output range into a 0 to 5 volt range of the ADC, right? So the signal conditioning takes this signal and converts it into a 0 to 5 volt signal. If we can do that, then the ADC will be able to use all the available levels to convert the temperature. So it will be able to use 256 levels to code for the temperature between 32 to 42 degrees Celsius. So this means that I can specify my signal conditioning circuit, right? I can say this is what I want my signal conditioning circuit to do. If this is my input voltage and my input voltage range is 320 to 420 millivolts, I want my output voltage to be between 0 to 5 volts. And you can write equations to do this conversion. And if you just assume a linear mapping, you get an equation like this. So output voltage is equal to 50 times the input voltage minus 320 millivolts. Okay, and you can build a circuit to do this, right? You need to make a subtractor and take away 320 millivolts and then multiply 50 and put a gain of 50 to the output of that subtractor. Okay, now if we do this, then how does our analog to digital conversion and the entire conversion of temperature look like? So so uh, so we've done this as we saw already. Okay, I'm just repeating the slides. Okay, here. So if we try to measure the resolution of temperature measurement now, what does it look like? So the resolution of our analog to digital converter, we said, was 19.5 approximately millivolts, right? So the resolution of the sensor output here that we are measuring is what? It's 50 times lower than that because we have amplified it 50 times. So you are measuring 0.39 millivolts approximately. And that corresponds to how many degrees Celsius? It corresponds to 0.03 degrees Celsius approximately, or 0.04 degrees Celsius, right? Another way to calculate that would be to say I'm converting 320 millivolts to 420 millivolts, which is approximately what? 100 millivolts range. And we are converting that, or we are dividing that into 256 levels. And you can get the resolution that way as well. And you can see that now our resolution of the temperature measurement is 0.04 degrees Celsius, which is more than adequate for body temperature measurement. So hopefully uh, this is kind of giving you some idea of how you specify signal conditioning circuits and how do you design and how signal conditioning circuits can actually help us design circuits that have less error and more resolution.